Hello everyone, my name is Zenan. I'm a student from Nanjing University in China. It's my pleasure to introduce our recent work about the quality assurance of the DNN model. And this is a joint work with my professors. The title is Operational Calibration, Debugging the Confidence Errors for DNNs in the Field. Firstly, I want to simply introduce some backgrounds. Over the past few years, similar to the rise of electricity by 100 years ago, AI is posed to transform the whole software industry. And recently, the deep learning technique has been widely adopted in many applications, such as self-driving, medical diagnosis, and so on. So, I think we can see that the trained DNN model are increasingly used as a software components. Especially on the Europes in 2018, some people have already called such software as Software 2.0. A typical example is using DNN model for medical diagnosis. Many groups have published on it. And the recent research in CVPR shows that the DNN model can nearly achieve radiologist-level performance. However, in this year's DCamp, engineers asked an interesting question. Since DNN systems work so well, why aren't these systems widely deployed to hospitals yet? And here we have an inconvenient truth. DNN models are usually trained by researchers in the lab with well-prepared training data. And those models perform very well on their test data, which are independently and identically distributed with the original training data. So, for researchers, the model works very well. However, in the real world, application engineers need to deploy this trained model into an application environment, where the data is distributed differently with the original training data. So, such a difference may lead to a significant drop in model performance. And in the perspective of engineers, model works badly. And in other words, the gap between the lab and the field causes the difference in the model performance. And in fact, it has been emphasized in a Nature comment. It says that one often overestimates how well the model will do in practice. And in machine learning community, such gap is called the domain shift. Actually, such shift is very common, but often ignored by researchers. So we believe that for a software engineer who want to deploy a well-trained model in an operation environment, it's necessary to perform some quality assurance activities to assess and improve the model, such that it can be well adapted to the operation domain, just like conventional software components need to be tested and debugged before putting them into use. And in this paper, we focus on debugging confidence errors in the field. As we know, for each input, a DNN model will usually produce not only a prediction, but also a confidence value for this prediction, which is actually the probability of prediction being correct. Confidence is very important in decision making. For example, let's consider a DNN model used for detecting lung disease. First, suppose the confidence is accurate. So, when the model gives a correct prediction of benign and giving confidence of 95%, everybody is happy and no further checking is needed. Second, if the model gives a false prediction of benign, as long as the confidence is also accurate, say 35%, no panic is needed, and in this case, the paper will do the confirmatory testing for sure. That's to say, accurate confidence can save the loss of wrong prediction. On the other hand, if the model confidence is not accurate, even though the model gives a correct prediction of by neg, the patient still needs to do the confirmatory testing, which is actually unnecessary. That's to say, incorrect confidence will make actual loss despite the prediction is correct. The worst is more than that. If the model gives the wrong prediction and also an inaccurate confidence, the doctor could believe this result because the model said that the result was very reliable. In this situation, some serious disease could be ignored and cause a disastrous consequence. So, we think the high confidence mispredictions are especially damaging. Unfortunately, here the inconvenient truth is that the gap between the origin domain and the operation domain, which is almost unavoidable in practice, and such domain will easily make the confidence produced by DNN models inaccurate. Here is a concrete example. For a DNN model trained on CIFAR 10, the rate of mispredictions in all high confidence predictions is 4.5% in the origin domain. It's very low, but if we apply it to an operation domain of STR10, the rate will increase by 10 times and reach 49%. So, what we want to do is operational calibration to debug those confidence errors, such that it can make the model well calibrated for operation domain. And note that here we do not want to change the prediction made by the model, but accurately tell how confident the prediction should be. In addition, there are some practical issues to consider. First, labeling operation data can be very expensive. For example, in an AI-aided medicine application scenario, one may have to use surgical biopsy to label a radiology image. And second, in many cases, the DNN model was trained by an independent third party, and due to the privacy and property concern, the original trained data are not available. So, we need an efficient and effective approach to operational calibration. Formally, given a previous trained DNN model M and a set of unlabeled dataset S, and we set the budget of labeling the examples in S by N. What we want to do is to find a confidence estimation function C hat to minimize the expected confidence errors. To solve this problem, we use the Gaussian process. Actually, what we want to do is to find the function C hat to minimize the Brouwer score, which is a standard metric for the accuracy of confidence. And there are three main challenges. The first is the labeled data in operation domain is very limited. And secondly, the input space for tasks such as image classification and natural language processing often has very high dimension. And finally, the problem is regression in nature, which is more difficult than classification, such as out-of-distribution detection. And to meet those challenges, we first use the Bayesian inference instead of usual regression model, which is more robust to overfitting. And we try to reduce the dimension by leveraging the representation learning capability of the DNN model. and this is the overall framework of our algorithm. First, we take the last hidden layer of the network as a representation space and work on this space instead of the raw input space. Second, we make clustering in the representation space to make full use of the locality of mispredictions. Finally, we build a Gaussian process for each cluster to compute the correlation for each confidence value. To further save the budget of labeling, instead of choosing and labeling the operational data all at once, we can use an iterative strategy. For details, every time we have a new labeled operation data, we can update the Gaussian process accordingly, and always choose the most informative example as the next one to label. And the Gaussian process naturally can provide the quantity of informative. The reason of using Gaussian process is that, firstly, it's a non-parametric Bayesian method, which can work well with a limited dataset without overfitting. Second, it can make full use of prior confidence. And in addition, the uncertainty can be quantified by the variance of Gaussian process to guide the selection of samples. Finally, we provide the evaluation of our methods. We want to answer two questions. The first is about the efficacy. Is our approach generally effective for different tasks, and how effective it is compared with alternative approach? And the second is about the efficiency. Is our approach be able to work efficiently with very small amount of labeled operation data? We conduct experiments on various datasets, including third-party transfer learning datasets, and some benchmark datasets with mutations to simulate practical usage settings. The scale of the models also vary from thousands of parameters to the tens of millions. In addition to image classification tasks, we also use natural language processing tasks. And we use two metrics to measure the efficacy of our approach, which are called Breadth score and LCE respectively. The Breadth score is actually the mean square error of confidence. It's a standard metric for measuring the performance of the calibration. And the LCE is the practical measurements for the loss due to confidence error. We compared our methods against the standard conventional calibration methods, such as temperature scaling, plus scaling, astonic regression. In addition, we also provided a method based on a recent proposal of this surprise adequacy. Although it was not proposed for confidence calibration, but we think it can be used to provide some novelty measurements of the inputs. From the results of Breadth score, we can see that our operational calibration outperformed all other methods significantly. And maybe LCE is more intuitive. Our approach reduced about half of LCE, which means that we save half of the loss when applying this technique in the field. The second question is about the efficiency of our methods. To measure it, we count the number of reducing high-confidence false predictions and the number of labeled operational data used. To illustrate our efficiency, we'll first try to use the fine-tuning to see how this method works with such limited data. The results show that The fine-tuning easily overfitted in the difficult tasks such as cipher and image clef. And even though we labeled the whole operation data to train this model, the overfitting could not be relieved. In addition, we also tried all the regularization tricks we know, but none of them could work. However, using our approach, we only need to label 1/10 of the operation data, and our approach reduced from 71% to 97% of high confidence errors. What's more, as can be seen from the figures, our approach has a nice property of taking effort very quickly. And also can be seen from this figure, our approach is very conservative, and this conservativeness was gradually remedied with more labeled data used. And here is the takeaway messages. Operational calibration is brought to reduce confidence errors for DNN model in the field. And I think the operational calibration should be taken as a necessary quality assurance step during the deployment of DNN models. And technically, it can be efficiently realized by building a Gaussian process on the representation layer of the DNN model. And finally, I want to end my presentation with Confucius' words. To know what you know, and what you don't know, that's a true knowledge. And this we want from DNNs in the field. Thank you.